Thank you very much for the invitation. It's always a pleasure to be physically in Marseille. And I also wanted to thank the organizers for all the efforts that they are putting in bringing together people from many different places. And I know that it takes a lot of energy to have this hybrid conference, and I'm really grateful for that. So today I'm going to talk about some joint work with Charlotte Perrin, who's also here, which started maybe, I don't know, two or 3 years ago. So I will present actually two sets of results that are connected around some propagation fronts in congestion models. So I will start by giving a little bit of physical motivations and explain to you what are the two models that we will be working with. So for each model, I will explain how you can build traveling fronts. So this is not so complicated because it's really an ODE, so it's actually fairly simple. But the issue will be to prove the stability of these traveling fronts in each model, okay? And so I will do that in the last two parts of the talk. So first let me tell you a little bit about the underlying physics. So the overall purpose is to study some problems in which there are congested zones, okay? So there are several examples in let's say, particle physics. So one example is multi-phase flows. There have been a lot of studies around crowd motion or herding problems in recent years. And the general observation is that so in flows in which there are congested zones on the one hand and non-congested ones, the dynamics in each zone are very different. Okay, so for instance, you have incompressible dynamics in the congested zones and compressible dynamics in the non-congested ones. So there are multiple issues. Okay, there are modelization issues because let's say there are several possible modelization of these congestion effects. And then you want to describe the transition between congested and non-congested zone. Is it, for instance, a free boundary problem, or is it something more continuous, I would say? And from the mathematical point of view, once you have chosen a given modelization, the issue is to analyze the model in which you have, for instance, a coexistence of the two zones. Okay, so here are some references on past works and importantly modelization papers on such a congested phenomena. Okay. So here I won't be talking at all about congestion models derived from particle systems. So I will focus only on continuous models, and I will distinguish between. So I will talk about two different models. One which is called a hard congestion model, and the other one which is called a soft one. So let me explain the difference between the two. So hard models are actually composed of two-phase flows. So I wrote an example here, which is not exactly the one I will be working with, but which is rather close. So here you have an equation for the conservation of mass. Here an equation which looks a bit like, let's say, the Euler equation, but you have a constraint. So the density rho is assumed to be between 0 and 1. And wherever the density reaches 1, which is its maximal value, the pressure is 0. Okay, so you have actually two zones. One zone in which rho is strictly less than 1. In that case, pi is 0. And you have a kind of compressible and pressureless dynamics. Okay. And you have another zone in which rho is exactly equal to 1, okay? And then the pressure is activated. The pressure is allowed to be non-zero. And then you have a kind of incompressible dynamics, actually. Okay? So it's and of course you have an interplay between the two zones. So this is a kind of, the boundary of the zone where rho is equal to 1 is free boundary type problem. And on the other hand, you have so-called soft models. So in that case, it's a one-phase flow, so you have just one flow with a very singular pressure. Okay, so here it's a compressible Euler type equation. Okay, there is no viscosity in these two models. Rho is still assumed to be between 0 and 1, but and actually this inequality is strict. And the pressure is, as you can see, is very small, except when rho is close to 1, where it might take larger values. Okay, and if you want to study the transition between these two models, you take the limits as epsilon goes to 0 of this soft model, and formally at least, you obtained this type of hard model. Okay. Okay, so this is exactly what I will be doing in the rest of the talk. So the two models that I will be working with are presented on this slide. So here V is actually the inverse of the density. Okay, so so V is always larger than 1 in that case. And so you have a 1D compressible Navier-Stokes type model with a little bit of viscosity here and with a singular pressure. Okay, so again, the singular pressure P epsilon is small everywhere when V is far from 1. And in the zones where V is allowed to be close to 1, P epsilon can take larger values and possibly infinity actually. And this model is endowed with some far-field conditions because so X is in the real line. So you assume that V epsilon goes to V plus and minus at plus and minus infinity, and same thing for U epsilon. Okay. So this model was studied by several authors, especially when the pressure is non-singular. So, for instance, by Matsumura and Nishihara, and more recently by Vasseur and Yao. And as epsilon goes to 0, formally what you obtain is a congested model. So it's very similar to the one that I presented in the previous slide, obviously. So in this model, so V is always bigger than 1. And when V is equal to 1, so when V is larger than 1, the pressure is 0. Okay, so you have these two sets of equations without the pressure pi. And when V is equal to 1, the pressure is activated in that congested zone, and then you have a type of incompressible dynamics. Okay. So the goal of the talk is to construct traveling waves for these two models and to show their stability. Okay. And also, I would say to study the asymptotic behavior, so to prove that the traveling waves for this model converge as epsilon goes to 0 to the traveling wave of this model here. Okay, so this is just what I said. Let me maybe point out a few difficulties. One of the issues is that, for instance, when you consider the model, the Navier-Stokes model with a singular pressure, so NS epsilon, this model becomes very singular in the congested zones, so when V is very close to 1. And when I say very close to 1, I will quantify that later on, but it's closer to, so V minus 1 is like some power of epsilon, okay? And so in that case, when we will construct global solutions, actually the vicinity of the traveling wave that I will be considering will be a ball of radius, which is like a power of epsilon, okay? So this result will degenerate as epsilon goes to 0. So here, even if formally this model goes to this one as epsilon goes to 0, it is it's not immediate at all that the stability, that you inherit some stability for the C model from the singular penalization one. Okay. So let me start with the traveling fronts. So I start with the traveling fronts for the limit system, which are the easiest ones. So I wrote again the limit system here so that you have it in front of your eyes. So I'm looking at solutions which are functions of x minus st, okay? And I'm looking at specific solutions which have the following form. So xi is my moving variable x minus st. And I'm looking for solutions which are such that v is exactly equal to 1 in r minus, and v is strictly bigger than 1 in r plus, okay? So xi negative is my congested zone, and xi positive is my free zone. And when I plug that into my, my system here, so first, the first equation immediately tells you that SV plus U is constant. Okay, so you get the Rankine-Hugoniot condition. The two asymptotic states need to be equal. And also for xi positive, you immediately get a logistic equation when you plug that into the second equation, because for xi positive, the pressure is 0. And so the logistic equation has well-known explicit solutions. So you know V completely explicitly in the non-congested zone. And since you have, you know the value of V at xi equals 0, because by assumption V is continuous and it's equal to 1 in the congested zone, you know V everywhere, okay? And you know that V has very nice properties. It converges exponentially fast toward this asymptotic state and so on. And the last thing that you need to do is determine the pressure in your congested zone. And this is done by looking at the jump condition. So you see that pi minus mu dxu over v needs to be continuous at xi equals 0. Otherwise, you have a Dirac mass, okay, when you derive with respect to x. And so when you, since you already know u and v in both zones, you immediately infer the value of p minus in the congested zone. Okay, so there you go. You have the, you know what the traveling wave looks like for the limit system. So it's a constant state on the xi negative, and it's a solution of the logistic equation in the other real line. Okay. Now let's look at the penalization model. So again, I wrote it here. And so once again, you look for solutions which are traveling waves, so which only depend on some variable x minus s epsilon t. Once again, you find that s epsilon v plus u epsilon is constant. Okay, so once again, you have a Rankine-Hugoniot type condition. And this allows you also, when you replace v by u in, or u by v rather, in this equation, you get an ODE for v epsilon. So this one is slightly more complicated, but it's still an autonomous ODE. So even if you don't have an explicit formula for it, it's fairly easy to determine, well, to prove first that a global solution exists, to study its behavior as xi goes to infinity or xi goes to minus infinity, and to prove monotonicity, uniqueness, and so on. Okay, so you know that this ODE has a unique solution up to a shift that's strictly increasing from v minus to v plus, and then to determine its asymptotic behavior, you have to prescribe something on the asymptotic states. Okay. So for instance, what I'm looking for here are solutions that converge towards the solutions of the of my limit system C, okay, as epsilon goes to 0. So for instance, I would like my asymptotic speed, my speed as s epsilon, to go towards some s, which is finite and non-zero, as epsilon goes to 0. And this more or less prescribes what my asymptotic state v minus should be. Okay, it's just it's given by a formula, so you can check this fairly easily. And so you find that essentially v minus up to some coefficient must be 1 plus epsilon 1 over gamma. Okay, and gamma was the exponent which was in the singular pressure here. Okay, p epsilon is epsilon over v minus 1 over gamma to the power gamma. Okay. Okay, and so if you do that choice, then provided you choose carefully your, say, your initial data, so the value of v epsilon at xi equals 0, so up to a choice of the shift, you can prove that the solution of this ODE converges towards the solution of the traveling front for the hard congestion model. Okay. So if you look at numerical simulations, so this here in red is the limit profile. So don't really look at the axis here. Okay, 0 should be here, but it's really, since everything is defined up to a shift, it doesn't really matter. So this this red solution is the limit profile. So equal to 1 on the negative axis and a solution of the logistic equation on the positive axis. And in blue and green, you have two solutions which correspond to different values of epsilon. Okay, so here you have the asymptotic value is always 1 plus epsilon to the power 1 over gamma. And so you see that if you lower epsilon, then you get closer, of course, to this asymptotic state. Okay. And if you zoom towards the transition zone, you get something like this. And actually, so what the convergence theorem that I stated, or lemma that I stated here is, so you can do a qualitative analysis and prove this fairly easily. But then you can also try to have a more quantitative description, at least in the transition zone. And so you can add some correctors to refine what happens in the transition zone, okay? Because obviously V epsilon has actually C infinity regularity, so it's a solution of an ODE, so it's infinitely smooth. And obviously it is not the case for your asymptotic profile, because your asymptotic profile, there's a jump of the derivative, okay? So you can correct this jump in the vicinity of the transition zone in order to have a more accurate description. Okay. So I won't go too much in details about this, but it is something you can do. Okay, so now let me say a few words about the traveling fronts for both models. So I will start with the penalization model. Okay, so if you want to study the stability of traveling fronts, it's a good idea to switch to the variables W and V. So W here is called the effective velocity. It's a combination of U and the derivative of logarithm of B. And so in variables V and W, the system looks like this. Okay? So now so what was proved, for instance, by Desjardins and Grenier is that you have some regularization on V through this dissipation term, which is somewhat hidden if you write the system in terms of V and U. Okay, so that's the first idea, switch to these variables. And the second idea is to actually, so this is maybe somewhat counterintuitive at first, so let me spend a little bit of time. If you want to investigate the stability of so in that case of traveling fronts, what you are going to do eventually is perform a fixed point type theorem in a high regularity space. Okay, so you are going to differentiate your system a large number of times and perform estimates, blah, blah, blah. Okay, so I'm going to do that in just a moment. But the first step is not that. The first step is actually to look at the integrated variables. So instead of differentiating my system, I'm integrating it. And why am I doing that? So it took me a bit of time. You can follow the computation step by step, but it has to do with the structure of the dissipative term here. So let me explain why. So maybe I can use the blackboard just for a moment. If you look at what you want to have in order to have a good structure of your dissipative term, you want to have a dissipative term which has a conservative structure. Okay, so if your unknown is say f or f epsilon, you want the dissipative term to look like dx of maybe some a, which is positive, dxf. Okay, this is a good dissipative term with a positive, because obviously if you multiply by f, and you integrate by parts, then you have a dissipative term that looks like that. Okay? So this is really the structure that you are looking for. And actually, if you look at the equation for V epsilon, your dissipative term is minus mu dxx of logarithm of V epsilon. And if I'm subtracting here, let's say, let me denote with the bar, this is the traveling front. Then, and let me set F epsilon as V epsilon minus V bar. Okay, so this is the quantity that I want to control. Then this is exactly minus mu dxx of logarithm of V epsilon over V epsilon bar, which I can rewrite as 1 plus F epsilon over V epsilon bar. Okay? And so this does not have the structure that is here because, well, it just doesn't, okay? So even, let's say that at first approximation, this is like minus mu dxx of F epsilon over V epsilon bar, okay? And for instance, if I multiply by F epsilon, then I won't have this nice structure there. I will have some kind of commutator, which is annoying when you do the energy estimates, and which prevents you from having, let's say, some global theorem, okay? On the other hand, if you integrate once, maybe you can switch down the lights. Thank you. If you integrate once, then the dissipative term takes this form, okay? And when you linearize it, so it's like minus mu dx of dx capital V epsilon over V epsilon. And then it has exactly this type of nice structure that I wrote here. So the reason why you go to integrated variables is really to prevent the apparition of any type of commutator within the diffusive term. Okay. Okay, so you work on the system for capital W epsilon, capital V epsilon, which is here. And here you are really going to perform a fixed point type analysis. Okay, so you have this nonlinear term that you write as so you linearize it when V epsilon is small. So the linearization looks like this. You are going to do the same thing here. You are going to linearize that term. And then you are going to treat all the quadratic terms that appear once you have linearized in a perturbative fashion. Okay? So this is really the general scheme. You're going to perform some weighted energy estimates in high regularity spaces. So the first step is to look at the energy estimates for the linearized operator and to check that the linearized operator has a nice structure, but you did everything you needed to do in order for it to have a nice structure, so it should be fine. Then you have to look at the commutators, because when you differentiate the equation, you kind of destroy the nice structure that you have. Some commutators appear, and so you need to control them. And of course, you need to look at product laws in order to control the quadratic terms. So I won't be talking about the last item at all because, okay, it's both, let's say, classical and technical. Okay, so I didn't think it was very interesting to present it here, but I will say a little bit about the first two items. Okay, so the linearized equation for capital W and capital V looks like this. Okay. And so now my dissipative term has this nice structure here. Okay, so if I multiply the first equation by minus 1 over P epsilon times F and the second one by G, and I integrate everything, then I get this weighted L2 estimate. So this is my energy. So you can see that minus 1 over P epsilon prime is this quantity, which is always positive. Here you have some dissipation term, which is also positive because this weight here is always positive. Okay, and dx v epsilon is positive also because v epsilon is increasing. It's a solution of a monotonous ODE, so it has a sign. Okay, so everything is nice because everything has a sign here. Okay, so this will typically be the type of energy I will be working with, and this will be my dissipation term. So a few remarks here. When you look at the weights that you have, they are always like some power of v minus 1 over epsilon, which means that when v is far from 1, so in the non-congested zone, okay, this is actually a very strong penalization, which means that you have a very good control of everything. Okay, but on the other hand, when you are in the congested zone, then v epsilon minus 1 is like epsilon to the 1 over gamma, and so this is a order 1, and this is actually a order 1 over gamma. Epsilon to some positive power. Okay, so this control is very bad in the congested zone. Okay, and this is really a source of loss in the energy estimates. This explains why eventually the size of the ball in which you are able to perform your fixed point is like some power of epsilon. Okay, so now let me explain how the sequence of estimates looks like. So this is the linearized operator for which I just showed you an energy estimate. This is the quadratic term. So again, I won't be talking about this one. It's just technical estimates. Okay, so you treat it completely perturbatively. The last thing that I need to explain is the structure of the commutator, okay? Because when you differentiate this equation, you slightly lose the nice structure that you had with this linearized operator because some commutator here is introduced. And so you need to understand how you can bound the commutator in order to close your estimates. Okay, so once again, this is your commutator, and this is exactly when you look at your the structure of your linearized operator. You're going to take the scalar product with this vector here. Okay, so you have a nice term which can be absorbed immediately in the dissipation. And you have another term which can be absorbed in the dissipation at a lower order because, okay, so this is the commutator when you look, for instance, at the first derivative, but this was the dissipation term that you had at the previous order, okay? But you see that you have a loss, okay? This is penalized. And so in order to absorb that into your dissipation at the previous order, you need to multiply, every time you differentiate, you need to multiply everything by epsilon 2 over gamma. Okay? Otherwise, you're not going to be able to absorb this dissipation term into this commutator term into the previous dissipation term. Okay? So you lose a power with each derivative. So this is really... This comes from several aspects. So once again, the fact that your estimates degenerate when you are in the congested zone, but it's also consistent with the fact that when you look at your profile v epsilon, okay, and when you look at its derivatives, you know that there is a jump in the derivatives for the limit profile, and actually. When you look at what happens in the transition zone, you can see that you have some small scale structures which are precisely of this size, which are precisely like epsilon to the 1 over gamma. So maybe it's consistent that actually you have this kind of penalization. Okay. Okay, so this is really, so this energy, so it's a kind of weighted H2 norm, so with a weight that depends on your profile, obviously, and also with a weight that is a power of epsilon. Okay, And so if you assume that your initial energy is in a small ball, so the radius of the ball is some power of epsilon times a small parameter delta, and if the parameter delta here is sufficiently small, but when I say sufficiently small, it's not it's smaller than some universal constant. Okay, it doesn't depend on epsilon anymore. Then you can prove that the nonlinear system has a global solution and that it remains within a ball of size epsilon to the 5 over gamma. And moreover, since you have a global solution, you can look at its long time behavior and you can prove that it converges as time goes to infinity towards your traveling wave solution. Okay. This is what I already said. So this assumption is very strong because obviously it degenerates when epsilon goes to 0. But we believe that it's kind of necessary because it's really due to the singularity of the pressure and to the form of the traveling wave solution. Okay, so for general data, at least, I'm not sure that it's so easy to weaken this assumption. So I will go over this again once I have talked about the other problem. Let me maybe just explain to you what I have in mind. It's possible that if you only perturb your initial data within the non-congested zone, okay, so far from the congested zones, at least for small times, you might be able to do something. But first, I have no idea how to do it as of now, and it's not completely clear. But okay, maybe there's a hope in this direction. But if you perturb your initial data within the congested zone, I believe that this type of assumption is necessary. Okay, so now let me go to the stability of traveling fronts for my model C, which is the limit model in which you really have 2 different zones. Okay, so a type of free boundary problem. And so maybe let me mention that this is still a work in progress. So I'm fairly confident about the theorem I'm going to state in a few minutes, but okay, this is not completely written yet. So again, I wrote down what the system is for the what the limit system is. So let me remind you, V is everywhere bigger than 1. When V is equal to 1, the pressure is activated, and essentially what you have is this equation. Okay, so a type of incompressible Navier-Stokes dynamics. And when V is larger than 1, then the pressure is 0, and so you only get the you get some kind of compressible Navier-Stokes. Okay, and so you had this traveling front solution, which was fairly simple because it was 1 and then the logistic equation. Okay, so following what I just said, so what I want to look at is the stability of this traveling front solution. And if you recall that in the soft congested model with the singular pressure, you had some trouble in the congested zone. For now, we just looked at initial data, which were perturbations in the non-congested zone. Okay, I'm not perturbing the initial data where in the zone where V is equal to 1. Okay, so I'm taking initial data, which are such that V is equal to 1 for xi negative. Okay, so no perturbation in the congested zone. But I allow myself to modify, to take an initial data, which is a perturbation of this traveling front, in the non-congested zone. So in the zone where V is strictly bigger than 1. Okay? And in that case, so the idea is that as long as you are not too far from a traveling front, your solution might look like this. So it might be something that is a bit like a traveling front, okay? So that moves at a speed x tilde of t, So, of course, the derivative of x tilde is not constant, so it's not exactly a traveling front, but it looks very much like one. Okay? And so you have an interplay between the dynamics of the solution and the dynamics of x tilde, which is actually exactly your free boundary. Okay? And so this is what we wanted to look at. So we want to construct solutions that have that type of behavior, that depend on x tilde. Okay. So we assume that the initial data is very close to the traveling front, okay, in H3. You also need some compatibility conditions at the interface that I'm not writing down, okay. And I didn't write that down either, but you also assume that V0 and U0 are actually equal to this Gothic U and V in the congested part, okay? And then you can prove the following. For small times, you can construct a strong solution of your congested system, which takes the following form. So there's a time missing here, actually. This solution is global, at least if the shock is not too large, say. So if V plus, which is the asymptotic state for V, is sufficiently, so if the left and right states for V are sufficiently close to one another. Okay. So let me say a few words about this. So first, you work in shifted variables. So by definition, my x tilde is such that for x lower than x tilde, V is equal to 1, U is equal to U minus. And for x bigger than x tilde, V is strictly bigger than 1. Okay? So this is the definition of what my x tilde should be. And so I work in shifted variables. So I didn't write down what it was. But this psi is x minus x tilde. Okay, so psi positive is x bigger than x tilde, and so on. Okay, because it's easier to obviously to work in a fixed frame. And once again, it's nice to look at the equation for the effective velocity W. So actually, the effective velocity W in the zone where psi is positive just satisfies the transport equation. So from this, you immediately infer that W is equal to W naught at psi plus x tilde. Okay, and in this zone, since in the zone where psi is positive, so x bigger than x tilde, by assumption, I'm looking for a solution such that V is bigger than 1 in this zone, so the pressure is 0. In that case, V satisfies this equation. Okay, with the right-hand side, that is the derivative of W. And since I know what W is when I integrate this transport equation, I immediately know the right-hand side. So you have a closed equation for V. Okay. And then, so like I said, you have an interplay between the dynamics of x tilde and the dynamics of the solution itself. And a way to understand this interplay is to look at the jump conditions for your solution at the interface. Okay, so your interface psi equals 0 is x equal to x tilde. So obviously you want V to be continuous at the interface, which means that so your shifted variable should be equal to 1 at psi equals 0. Okay. And when you differentiate the identity V of t, x tilde of t equal to 1 for all times, you get this type of, let's say, ODE for x tilde. Okay, so let me, so this is just the differentiation of V at point t, x tilde of t equals 0. Okay. And you also want the jump of U to be 0, so this prescribes a Dirichlet type condition for you. Okay. The other ingredient is that because of the conservation of W, you have this. So you get this algebraic relationship between for V. And so when you plug this back into this equation, you get a type of ODE for x tilde. Okay. So now let me explain what happens. If you know what x tilde is, then here you have a transport diffusion equation for V, and you can construct a Vs. Okay. So if you know x tilde, you can construct V. And on the other hand, if you know what V is, then you can construct a U. I will explain to you how in a minute, but U also satisfies a transport-like diffusion equation. Okay, and so if you know U and V, then you get an ODE for x tilde, or a type of ODE, let's say a dynamical system for x tilde, which is given by this formula. Okay, and so you see where I'm going here. You're going to construct a solution of the whole system as a fixed point, exactly as in the Cauchy-Lipschitz theorem. Okay, so I put ODE in quotation marks here because, okay, it's not exactly an ODE because x tilde prime at time t actually does not only depend on x tilde, but it depends on the whole history of your solution. So it depends on your whole solution between 0 and t. Okay, so it does not only depend on the value of x tilde at time t. So it's not exactly an ODE, but for the Cauchy-Lipschitz theorem or its variants, this really doesn't matter. It works exactly in the same way. Okay. So the strategy is to construct x tilde as the fixed point of this application. So capital A here. So like I said, you take a function y tilde, which is smooth enough, so say in H2, okay? You construct a solution V of this transport diffusion equation, okay? So if y tilde is given, this, so it's a non-linear, but it's a fairly nice transport diffusion equation, so you can construct rather strong solutions and have nice estimates on it, okay? So with this Dirichlet boundary condition. And once V is constructed, then you can construct this U, which, this should be Dixi. So this U again satisfies a transport diffusion equation. The equation for U is linear once you know V, so it's even simpler. Okay. Okay, and once you know V and U, then you can define Z tilde, which satisfies this ODE. Okay. So Z tilde depends on Y tilde and on the solution that you just constructed. And the X tilde that you're looking for is nothing else than the fixed point of this application. Okay? So you want to find some assumptions which ensure that A tilde is a contraction in the space H2. And so the core of the proof is to have these so estimates for VS and US, because eventually this is what will allow you to prove contraction for this application A. Okay, and so let me slightly explain. So what you can prove is that the error between or the difference between the solution that you constructed and your traveling wave is controlled by the initial data and by the difference between y tilde prime and s in H1, but in the following way. So you can always manage to have a small constant in front of the second derivative, okay, arbitrarily small. So obviously in that case, the C will be actually like C over delta, something like that. And
hello.
Oui. Qui parle? Allô? C'est un peu.
Le son de mon ordi il est à chier, hein, donc vraiment là ça va pas.
Hello? Je ne sais pas si c'est quelqu'un qui est au téléphone.
Ouais. Attends, parce que là il est où? Il est sur l'écran.
D'accord, ok. Okay, so when you perform these estimates, so what you want? Oui.
Can you hear me?
Yes, I can.
Yeah, it's from. Okay, it's from this. Great, great. Okay, so hi. Yes, who wants to start? We prepared a few slides to explain. So since yesterday, we thought about the problem and how to really define it.
Bon, attendez, j'attends un peu. Mais si, je pense que c'est quelqu'un dans une autre salle aussi, à mon avis. Ben non, parce qu'il n'est pas dans notre salle. Mais je pense que c'est juste que c'est le son d'une autre salle qui est balancé sur nos haut-parleurs, mais c'est une erreur. Okay. So what you want eventually is to you want to have since you want to have a contraction, okay? You want this constant here to be small, and there are two ways to do that, at least as of today, from what we understand. The first way of having a small constant here is to take a small time, and you essentially do a Poincaré inequality, and then you gain a power of time. And so this is one way to have a small constant here. And the other way, actually, this is a bit hidden, but here this constant depends on v plus minus 1 because it depends on the size of the derivatives of your traveling wave. So it depends on dxv or dxv bar. Okay. And this is actually proportional in some way to v plus minus 1. So if v plus minus 1 is sufficiently small, then you can get this constant as small as you want and you get a contraction. Okay, so this is the reason why you have these two types of assumptions. On the one hand, for small times, you always get a unique solution because you have this Poincaré inequality, and this is another way to ensure that you have a global solution. Okay, so I'm reaching a conclusion now. So to sum up, so I presented two models. One a soft congestion model with a singular pressure and its associate limit system, which is a hard congestion models. In traveling fronts for the singular model, you have a sharp transition between congested and non-congested zones, which you can describe in a fairly accurate way, even if I didn't insist too much on that today. When you study the stability of traveling fronts within the singular model, you can do a very quantitative analysis, but which unfortunately degenerates as epsilon goes to 0. And when you study stability for traveling fronts for the hard congestion model, you can do that as long as you take initial data, which are perturbations only in the non-congested zone. Okay. And so an obvious perspective is to allow for perturbations within the congested zone and to understand what happens if you take a small bump in the initial data in the zone where v is equal to 1. Okay, what happens in that case? Do you create some traveling waves in some way? I don't know. And so the other question is when v plus minus 1 is large, so if you don't have a small shock but a large shock, so in that case, in the last theorem that I presented, you only have you can only construct local solutions that have this type. And so I don't know what happens in that case. Do you have some kind of singularity formation? Do you lose that nice structure where you have a separation, well, a kind of extended traveling wave, say, because you instead of moving at constant speed, you move at a speed x prime of tilde, but it's still very similar to what happens for traveling waves. Okay, so this is kind of open. I don't know how it will work. So if there are suggestions, I think we would be very happy to hear them. So thank you for your attention, and I will stop here.
And when you send it, for your talk. Are there questions, remarks, comments? Maybe first here in Lumini. Charlotte? No. And elsewhere? Are there? Ah, Boris. Sorry.
Okay. Bon, avec le micro, voilà. Yes, about your result of the stability of the traveling wave, I assume that the smallness condition depends on the viscosity, probably.
Yes.
Do you think that it's possible to do something which is uniform in terms of the viscosity and maybe to pass to the limit when the viscosity goes to 0?
I'm not sure. I think we use a lot the dissipative structure of the equation, to be honest. So we did. I'm not sure we tracked down every single dependency on the viscosity. I'm not sure. So for the one with the singular pressure, I guess you're thinking. The other
yes.
one, I think
yes.
we're too far from it. But I guess if you allow, so it's possible. So let me go back a bit. Okay, so here actually I cheated a little bit. So this is the form of the energy. You also need to add some coefficients, okay, which are small enough so that you get so that the dissipation term is actually absorbed into the rest, okay. My guess is that, of course, these coefficients will depend on the viscosity. You can probably track down the dependency. And so in the end, what you will get is that the size of your ball will depend on epsilon and on mu. And I'm sure that you can have some quantitative estimate on the two. So it will be like a power of mu, probably. I guess. Okay. And then if you want to have something that is completely uniform in mu, we didn't try it, but I think it wouldn't be that easy.
Just maybe very short questions. On your last result, do you think it's possible to use the technique of Alexis-Vasseur, for example, or the technique of relative entropy when you have your X style T? Or is it possible to use this type of technique maybe?
So you're thinking for the energy estimates?
Yes, for the result.
Yes, this is more or less what we're doing actually. When we do when we do the energy estimates, I think this is already what we are doing, because you need to compute, at least for some of the energies. Since the equation is nonlinear, you need to do things in to be careful about the type of energy that you're constructing. And I think what we're doing is exactly a kind of relative entropy estimate. So yes.
Thank you.
So no other questions? Nobody? Okay, so we thank the speaker again.